Hello, guys. You are welcome to the platform. My name is Green, and today we are going to be looking at a very interesting topic in physics. And that topic is really essential in both physics and even in chemistry, actually, uh, as well as some other courses in higher physics, solid state physics, quantum physics, and all of that. That topic is what we call photoelectric effect. It is very, very essential in physics. Um, it is this experiment that actually led us to a new knowledge in physics, which is quantum mechanics. So in today's video, we are going to be talking about everything you need to know as regards photoelectric effect, from the meaning of photoelectric effect, the deductions from the experiment, how this deduction cannot be explained by classical physics, how quantum physics now explain this particular deduction. We talk about the Einstein equation, which gave him the Nobel Prize award in 1921, and everything you need to know about this topic will be discussed here in this video. So sit tight and make sure you watch till the end of the video. So let's begin. Photoelectric effect. Photoelectric effect. I'm going to come with the explanation of what that guy implies from two different perspectives. So let's start from the first perspective here, which is emission of electrons. So I'm going to be starting from the perspective of emission of electrons. So electron is a negative charge, and metals generally are made up of free electrons. So if I have a metallic material, we have free electrons inside this material. Now, there are so many ways electrons can be emitted from a metal. There are so many ways electrons can be ejected or liberated from a metal. Some of the methods that can be used include thermionic emission. So there's something called thermionic emission. Thermionic emission is the liberation of electrons from a substance, from a metal, through the application of heat energy, thermionic emission. We have field emission. It is possible to also emit electrons from a metal. It is possible to liberate electrons from a metal by the application of strong electric field. So if I have the metal in the presence of a strong electric field, it is very possible to be able to liberate electrons from the metal. We also have what we call secondary emission. Now, it is equally possible to liberate electrons from a metal when we bombard that metal with high energetic particles, with high energetic materials. So when I bombard a metal with high moving or fast moving or high energetic materials, then electrons can actually be ejected from this particular metal. And the last guy, which is our focus for this lesson, is photoelectric emission. Photoelectric emission. So from the word photo means light, then electric here is talking about electrons. So it means that it is also possible to emit or to liberate electrons from a particular metal when when it is incident, when that metal is made to be incident or it's exposed, when that metal is actually exposed to light, to radiation. Light here is talking about radiation. So when a metal is exposed to a radiation, or when light is incident on a metal, light of a particular frequency or a particular wavelength, when it is incident on a metal, it is possible to also liberate electrons from that metal. So these are the different ways we can liberate electrons. We can eject electrons. Electrons can be ejected from a metal surface. These are the different ways we can achieve that, either by application of thermal energy, that's thermionic, or application of strong electric field, as field, or bombardment of that metal with high energetic materials, that's secondary emission, or the exposure of that metal to radiation of a particular frequency or energy. So our focus for this lesson is this fourth guy, which is photoelectric emission. So from the word photoelectric effect is just a phenomenon or a process of liberating electrons from a metal when that metal is what is exposed, when that metal is exposed to radiation, to light of a particular frequency. So we are saying that if I have a metal here and we expose that light to radiation, then electrons which are embedded in this metal here can be ejected. So this is radiation of a particular frequency and wavelength, when it is incident on the metal and electrons are being emitted. That process is what we call photoelectric effect. That is what we call photoelectric effect. So these electrons are ejected. The electrons are ejected due to this light being incident on this metal. Now, the electrons that are ejected here are called photoelectrons. The electrons are called photoelectrons. The electrons that are ejected due to this process are called photoelectrons. So that is what we call photoelectric effect. But let's move it back a bit. Now that we know the meaning, let's go back a bit to the experiment itself, because this experiment was actually conducted before we realized that, oh, it's possible for electrons to be emitted from a metal when it is incident when light is incident on that metal. So let's talk about the experimental deduction. The experimental deduction of this experiment, because it is actually an experiment that was carried out to actually further explain what light is all about. So this experiment was carried out, and we realized that by using our knowledge of classical mechanics or classical physics, meaning if we understand light to be a wave only, we will not be able to explain the deduction from this experiment. So what are the experimental deduction from this experiment? We know the experiment involves the fact that if I have a metal and light of a particular frequency is incident on that metal, because this metal is made up of electrons, the electrons can be ejected. These electrons are called photoelectrons. But what are the experimental deduction from this particular experiment? The first experimental deduction from this experiment is the fact that the photoelectric effect is an instantaneous process. It is an instantaneous process. This implies that there is no time lag, there is no time delay between the incidence of this radiation on the metal and the ejection of the electron. Immediately this light is incident of the metal, so far as that light is up to the threshold frequency, which we are going to talk about, so far as that light is up to a certain amount of frequency value or a certain amount of wavelength value, then the electrons will be ejected immediately. It's an instantaneous process. That is, there is no time lag. In fact, experimentally, we realized that the time interval between the incidence of the radiation on the metal and the ejection of the electron is approximately 10 raised to the power minus 9 seconds. That's about 10 nanoseconds. So that means that it is a process that occurs immediately. Because it is this light that is incident on this particular metal. It's not a wave. This light is actually a particle. So it was in 1905 when Albert Einstein actually wrote his paper, that is his miracle year. He wrote his paper to explain this photoelectric effect and explain to us that when that light is pictured as a particle that is made up of discrete quantity of energy, meaning discrete packet of energy. If we picture this light as a particle that is made up of discrete amount of energy, such that each of these guys are interacting, each of them will interact with a particular electron. If we can picture this light like this, then we will be able to see the reason why this process is an instantaneous process. But when we see light as a wave, we will not be able to explain this. That is why this process cannot be explained. This experiment cannot be explained using classical physics. It can only be explained using quantum mechanics. So if you picture light as a particle, and this particle is called a photon. So light is made up of a particle called photon. This photon is just discrete packet of energy. So this light has an amount of energy which is hf. The light, the radiation, has an amount of energy hf, where h is the Planck's constant and f is the frequency of the light. So once this light is incident on this metal surface, the electrons will be ejected immediately, so far as this frequency is up to a particular amount, which we are going to talk about. So that is the first experimental deduction for this photoelectric effect experiment. That is the first deduction we can get from there, that it is an instantaneous process. We don't need to wait for the electron to absorb the energy before they are ejected. No, that process occurs instantaneously. Number two, the second experimental deduction is the relationship between the intensity of that radiation and the kinetic energy of these photoelectrons. So the second deduction is that the kinetic energy of the photoelectrons, is independent of the intensity of the radiation. So what are we saying here? When these electrons are ejected, when we have these photoelectrons being ejected from the metal, they can move off. If they have sufficient energy, they will move off with a particular kinetic energy. Now, the second deduction is telling us that if we change the intensity of the radiation, if the intensity of the radiation is changed, there is nothing that will happen to the kinetic energy of the electron. The kinetic energy of the photoelectrons does not depend on the intensity. The intensity of the radiation is talking about the energy of the radiation per time per unit area, meaning the power of the radiation per cross-sectional area. Now, this intensity of the radiation has no effect on the kinetic energy of the photoelectrons. The only thing that will affect the photoelectron, or the only thing that will affect the kinetic energy of the photoelectron, is the frequency or the wavelength of the radiation, and that is the third deduction. So the third deduction is the fact that the kinetic energy of the photoelectrons depend upon the frequency or the wavelength of the radiation. So it is the frequency or wavelength of the radiation that actually affects the kinetic energy. We are going to see the graphical representation of this deduction. It is the frequency of that light or the wavelength of that light that affects the kinetic energy of the photoelectrons. So when we change the frequency of the light, the kinetic energy of the photoelectrons will equally change. When we change the wavelength, of course, wavelength is related to the frequency. The frequency is C over lambda. This is the frequency of of this our photon, of this our radiation. The frequency is C over lambda, where C is the speed of light in air, the speed of this guy, of the radiation in air, which is a constant. C is 3 times 10 raised to the power 8 meter per second. So the deduction here is that the kinetic energy of the photoelectrons ejected will only be affected by the frequency or the wavelength of that incident radiation. Now let's look at the next deduction, which is another essential deduction. The deduction is the fact that no photoelectron photoelectrons will not be ejected. Photoelectrons will not be ejected. Photoelectrons will not be ejected if the frequency of the radiation is less than a particular value. Where that F naught is called the threshold frequency. a minimum frequency. So that means that there is a condition. We are not saying that immediately we have light incident on the metal, that electrons will be ejected immediately. No. There is a condition that must be satisfied. These electrons will only be ejected if the frequency of that radiation is up to a particular value, is up to a particular amount. If the frequency of the radiation is less than a cutoff value, there's a cutoff. If the frequency of the radiation is less than a cutoff value, then the photoelectrons will not be ejected. There will be no photoelectric effect. Unlike classical mechanics, so this is just the idea. In classical mechanics, in the world of classical mechanics, where we believe that light is just a wavefront that transfers energy continuously. If we use that word of classical mechanics to try to explain this experimental deduction, we will not be able to see why all of these things happen. So that means that classical mechanics cannot be used to explain this experiment. Viewing light as a wave cannot be used to explain this experiment. But when we view light as a particle, then we're able to explain this experiment. Our deduction quantum mechanically actually aligns with these experimental deductions. So according to classical mechanics, we don't need a threshold value. We believe that when light is incident, no matter the frequency of the light, once that light is incident on a material, the material just begins to absorb that light, and when it gets to a particular value, then the electrons will be ejected. But experimentally, when we perform that experiment, we actually realize that that frequency must be up to a particular amount before electrons can be ejected from that metal. So these are the experimental deduction from the photoelectric effect experiment. These are the experimental deductions from the experiment. All right, so let's take a look at the Einstein equation. The Einstein equation for photoelectric effect. So in 1905, like I said, Albert Einstein wrote a paper, and in his paper, he actually gave us about 4 statements about different areas of physics. That is where he wrote something about special relativity as well. But he did not get a Nobel Prize in physics for his work in special relativity. He actually got the Nobel Prize for his work in photoelectric effect, meaning the equation I want to write now is what won him a Nobel Prize. Now, what is this equation all about? All right, so Albert Einstein told us that if I have, let's say we have a material. Let me still use a glass block. This is the glass block. Then light, which is seen as a particle, these are the photons, is incident on this metal. I said glass block, a metal, not glass block, a metal. We have electrons embedded inside this metal. This is light. I'm using this so that we can picture it as a particle. So this is the light, and these are the photons. Now, these photons, this radiation source, this is the radiation or light. It has an amount of energy E, right? Then, when this guy is incident on this metal here, the first thing that will happen is that it will tend to, this radiation, this energy, the first thing it will do is to overcome the surface barrier holding these electrons back. So that means that there is something called the work function. So light of a particular energy, radiation of a particular amount of energy is incident on a metal. The first purpose, the first function of that energy is to break the barrier, is to break that surface barrier that is holding these electrons hostage. It is to break this barrier that is holding this electron here. Now, the electrons are being held hostage in this material. They cannot go out of this material because of the surface energy, the surface barrier. Now, the minimum amount of energy that is needed for these electrons to be ejected to the surface, the minimum amount of energy that we need to supply this metal so that the electrons can be ejected to the surface is what we call the work function, phi. So work function is the minimum amount of energy that a material, that a metal requires for electrons inside that metal to be ejected to the surface of the metal. So the first function of this radiation, of this energy here, of the light, is to supply the energy, the minimum energy that is needed for these electrons to just go up to this surface here. And that minimum energy needed to eject electrons are inside. The minimum energy needed to break the surface barrier of that metal and allow electrons to be ejected to the surface is what we call the work function. And this work function is actually given to be hf naught. The work function is given to be hf naught, where h is the Planck's constant, and the value is 6.626 times 10 raised to power minus 34 jouleseconds, and f naught is the threshold frequency. So what is threshold frequency? Threshold frequency, or the cutoff frequency, is the minimum frequency. The minimum frequency that the radiation must have. The minimum frequency that light coming from the source must possess before electrons can be ejected, before electrons can be liberated, is called the threshold frequency. The minimum frequency needed. Minimum frequency needed for photoelectric effect to occur. So we are saying that if this light is coming and this light has a value of has a frequency of 100, or let's say 10 raised to power 7, let me assume 10 raised to power 7 Hertz. If this is the frequency of that light, then the the threshold frequency must be up to that value or less than that value. So we are saying that the frequency of that light, before that radiation can eject the electrons from this metal here, that light must have a frequency that is up to an amount. That minimum frequency is what we call the threshold frequency. So that means that the threshold frequency of that metal must be this value or less than the value of the frequency of the light for photoelectrons to be ejected. So that is what we are saying here. So threshold frequency is the minimum frequency that light must have for electrons to be ejected. And this this work function, which is a function of the threshold frequency, is a property of the material. So that means that it varies from material to material. The work function for a tungsten metal is different from a thoriated tungsten metal. So it is also different from an oxide coated metal. So we have different different values of work function depending on the material we are considering. It varies from material to material. And before a material can be used for electron emission, it should have a low work function, because work function means minimum energy you must supply to that metal for electrons to be emitted. So that means that if I have a metal of very high work function, then I will need to supply high amount of energy before electrons can be ejected, can be liberated from the metal. So this is the work function of the metal. Now we know that there is a connection between frequency and wavelength. I've shown it that frequency is actually C over lambda. So that means that I can also write this work function of the metal to be in terms of wavelength, and that will be hc over lambda. So if this is f naught, then I will write this as what? Lambda naught. So work function of a metal, of a material, is hf naught, and it can also be hc over lambda naught. What is this c? Our speed of light in vacuum, 3 times 10 raised to 8 meters per second, and lambda naught is the threshold frequency. Threshold wavelength. Lambda naught is the threshold wavelength in meters. F naught is the threshold frequency in hertz. Lambda naught is the threshold wavelength in meters. Now look at the relationship between F and lambda. F and lambda are inversely proportional to each other. So that means that if we are saying threshold frequency is the minimum frequency, if threshold frequency is the minimum frequency needed for photoelectric effect to occur, F is inversely proportional to lambda. So if threshold is the minimum frequency that light must have before photoelectric effect must occur, that means that threshold wavelength must be the maximum. Threshold wavelength is the maximum wavelength. The maximum wavelength that is required for photoelectric effect to occur. The maximum wavelength that light must have for photoelectric effect to occur. Threshold frequency, the minimum frequency. That means that if the radiation we are using has a frequency lower than the threshold frequency, there will be no photoelectric effect. Similarly, if the radiation we are using has a wavelength higher than the threshold wavelength, then there will be no emission or ejection of photoelectrons, because threshold wavelength is the maximum wavelength, the highest wavelength. In fact, we don't use high or low for wavelength. We use long and short because it's length. So threshold wavelength is the longest wavelength required for photoelectric effect to occur. So that means that light must have a wavelength of that threshold value or any value less than the threshold wavelength. Then in terms of frequency, it must have that frequency value or any value higher than that frequency value. So that is the work function. So before we can eject electrons, the minimum energy needed to eject these electrons is what we call the work function. The minimum energy needed is called the work function. So let's go back to the Einstein's equation. So what he said was that, okay, if I have light radiation of a particular energy E, the first thing that energy should do is to supply the work function for that particular metal. E will supply the work function. So the remaining amount of energy will now be used up by these electrons that have been ejected as their kinetic energy. So meaning that our E should be equal to the work function phi plus kinetic energy. Now listen up. If, for instance, the energy of the radiation is 10 electron volts, if the energy of the radiation is 10 electron volts, then the work function of the metal is 7 electron volts, then that 3 electron volt that is left does not mean that it will be the one that will be used as a kinetic energy. I want to explain a particular concept here. If this is the energy of the radiation, then it is possible that and the work function is 7. So what is possible is that the remaining 3 can be used as kinetic energy of the photoelectrons ejected, or the remaining 3 can be lost. The remaining 3 can be lost in form of heat, in form of collision. So the remaining 3 can be lost, the remaining 3 can be used as kinetic energy. It depends. So our focus will be on those electrons that will not collide. Those electrons that will not collide with themselves or with the walls of this metal, such that there will be minimal loss of energy. So that means that we want only the electrons, he considered only the electrons that we have the maximum possible kinetic energy. So what you should understand is the fact that this remaining energy here does not automatically become the kinetic energy. The remaining energy can be lost completely in form of collision energy or in form of heat loss due to that collision. Or the remaining energy can now be converted to kinetic energy depending on the electron. That is why our target is usually electrons that are closer to the surface, so that they can easily go to they can easily be ejected, and not the electrons that are down this material. Because if the electron is so down this material, before the electron can get to the surface, the electron will collide, and some of this energy, the remaining energy here, can be lost in the process. So that is why in the relationship, in the equation, we don't just call this the kinetic energy. We need that the maximum possible kinetic energy. Now, it is also possible that out of the remaining three, maybe it is 1 electron volt will be lost and another electron will now use 2 electron volts as its own kinetic energy. We can have a situation where out of, let me make it a better table. So we have 10 electron volts as the energy of the radiation. We have different situations that can occur. If the work function of the metal is 7 electron volts, we have 3 different situations here. Then we are saying that it is possible that some particular set of electrons will lose the entire 3 electron volt that is left and there will be no kinetic energy. It is possible that some certain class of electron will lose, let's say, only 1 electron volt and we now have 2 electron volt as their kinetic energy. And we can also have some certain set of electron that will not lose anything, or the significant loss, the loss might be insignificant, very close to 0, while they will now use the remaining 3 as their kinetic energy. Our concern, our focus, what we want is this set of electrons. The set of electrons that will not lose the remaining energy in form of collision energy and the likes, and we use the remaining energy as the kinetic energy of the photoelectrons. This is the case that we need, and that means this is the case where we can have maximum kinetic energy. So what I'm saying in essence is that in this equation here, E equal to 5 plus, it is not just the Ke that we are using here, it is the maximum. The maximum possible kinetic energy is our focus. So this is the Einstein equation, that the radiation energy, the energy of the light, the energy of the incident light is equal to the work function of the metal plus the maximum kinetic energy of the photoelectron. So E again is the we can call it the photon energy because the light is made up of photon, so it can be called the photon energy or the energy of the incident radiation. Energy of incident radiation, the energy of incident radiation in joule, it can be in joule or electron volt. I will show you the relationship between joule and electron volt. And phi is the work function. Phi is the work function of the metal. Work function of the metal in joule or electron volt as well. While Ke max is the maximum kinetic energy. Maximum kinetic energy of the photoelectrons. The electrons that are ejected. The maximum kinetic energy. Alright. So that is what Einstein gave us. Now let's work on this equation. Let's work on this equation and see some key things from this equation. Alright. So if I make Ke max subject of the formula from here, Ke max, the maximum kinetic energy, will equal to E minus phi. That means Ke max will be equal to, of course, before that, what is our E? E is actually HF. And what is our phi? Phi is HF naught. That means our Ke max is actually HF minus HF naught. So if you look at this now, this looks like a straight line equation. So if I compare this equation, if I compare to y equals to mx plus c, then I can plot a graph of Ke max against frequency. Remember, in our experimental deduction, what affects kinetic energy is the frequency or the wavelength. The frequency or the wavelength will affect kinetic energy. So this is a straight line equation showing that what we have a linear relationship. There is a linear relationship between the maximum kinetic energy of the photoelectrons and the frequency of the radiation. Now, if I plot this graph of Ke max against, if I plot the graph of Ke max against the frequency, if I plot the graph of Ke max against frequency, so it's a straight line equation and there's an intercept here. The intercept on the y-axis is, if you compare, where our y is Ke max, our y is Ke max, our f is this x, that means our x is f, Our m is h. The gradient will be h, and our c is negative hf naught, which is what's it called, the intercept on the y-axis. So that means that if I plot the graph, it's going to look like something like this. This is the graph of Ke max against the frequency. It will be a straight line graph. It will be a straight line graph. A straight line graph. If I find the slope of this graph, the slope of the graph, which is tan, if I have this angle as theta, tan theta will be, what is the slope directly? The slope is the Planck's constant. So this is one way we can actually verify the value of the Planck's constant h. Now, this is where this graph cuts the y-axis, the Ke max axis. That means that's the intercept on the Ke max. And what's our intercept now? The intercept is minus hf naught. So the intercept on the Ke max axis is minus hf naught. Now, there is a cut here as well. The graph also cut a point on the f axis. When our K is 0, when Ke max is 0, our f here will be f naught. So the intercept here, because how do you find the intercept here? If my Ke max is 0 at this point, so what is my value of f at this point? If I put Ke max at 0, 0 equals to hf minus hf naught. So I'm looking for f value. So that means if I transfer this, hf naught equal to hf. H cancel h. That means f is what? F naught. When Ke max is 0, f is f naught. So that is to tell us that the intercept on this guy here is the what? Threshold frequency, which is understandable because if you go before this threshold frequency, if f is less than threshold frequency, what is our kinetic energy? Negative. If I trace it down, I have negative. The graph is at the negative side. When f is less than f naught, the graph is at the negative side. Our Ke max is negative, telling me that what? The electrons are just inside the what? The metal. The electrons are not even ejected to the surface. Talk more of what? Moving with a kinetic energy. They are inside. Photoelectric effect will not occur at this area here. This area here, it will not occur at this area here. So this is a graph that tells us the relationship between Ke max and what? The frequency. Now we can also plot this graph in terms of the maximum kinetic energy and the wavelength. We can also do that plot, make that plot as well. So from here, remember that f is c over lambda. If f is c over lambda, that implies that means that this equation, let me make it equation 1, since f equal to c over lambda and f naught is c over lambda naught, then the formula becomes Ke max equal to hc over lambda minus hc over lambda naught. So that means that if I plot the graph, if I plot a graph of Ke max against 1 over lambda, I'm going to have something like this. So in terms of wavelength, we can have something like this. In terms of wavelength, I will plot Ke max against 1 over lambda. Of course, this frequency here is in hertz, don't forget. So if I plot this against 1 over lambda, I'm going to have the same kind of graph. Because if you look at this, we compare this to y equals to mx plus c. So if I plot y equal to mx plus c from here, compared to y equals to mx plus c, this is why 1 over lambda is the x. Then here I have my c. So I'm going to have that same straight line. I'm going to have that same straight line here. And if I find the slope of this graph, the slope theta for the graph, the slope will be tan theta as usual. And tan theta will be what? What's the slope here? It's going to be hc. The slope will be hc this time around. It's going to be hc. And where is this guy cutting on this axis here? It is cutting, our c here is what? Negative hc over lambda naught. And what is this value here? This value here is going to be c over lambda naught. Or let's see, it's going to be 1 over lambda naught. Because c we cancel c. So that will be our what? Graph. This is what the graph will look like if I plot Ke max against 1 over wavelength. I'm going to have my graph like this, which is also showing me that what is still a what? A straight line graph. It's a straight line graph. That's the relationship between the maximum kinetic energy and the what is it called? And the frequency or the wavelength of that radiation. So that is what Einstein is talking about. All right, so let's look at another concept very quick. Let's see another concept very quick. Now, in the deduction we gave, in our deduction, the experimental deduction of the photoelectric effect, we explained that the maximum the kinetic energy of the photoelectrons, which is the maximum kinetic energy of the photoelectrons, is not affected by the intensity. The maximum kinetic energy of the photoelectrons is not affected by the intensity of the radiation. It is only affected by the what? The wavelength or the frequency of the radiation. So the question is now, what then affects the intensity? Or what does the intensity affect? Let's put it that way. What will the intensity of the radiation affect? All right. So if let me show the experiment using another form of diagram. So if I have a vacuum tube and I have a plate here, which is our emitter. If I have my emitter here, a plate that will emit the light, usually the cathode. If I have my rheostat connected to my battery, here, I have my ammeter here, then I have my collector, which is the plate. The collector, the plate, connected like so. So if I make a small perforation such that my radiation can be incident, this is the radiation source. It is incident on this emitter. This is the emitter, which is the cathode. And this is the collector, or the plate, or the anode. So what we are saying is that if F is up to the threshold or greater than the threshold, if the frequency of the radiation is up to the threshold frequency or even greater, then once it is incident on this metal, immediately electrons will be ejected. Electrons will be ejected, right? Electrons will be ejected. So electrons will move towards the collector here. We go towards the collector here. Of course, this place is connected to the positive leg. This is connected to the negative leg. All right. Electrons will be what? Ejected, and they will move towards this plate, the collector. Now, when the electrons move, of course, the electrons will be moving like this. Electrons will be flowing like this, and conventional current will be flowing in this direction. This will be the direction of flow of conventional current. Electron flow in opposite direction as the conventional current. So current will flow. This is the ammeter to measure the amount of current that will flow. Right? Now the current that flows due to the movement of these photoelectrons. These are the photoelectrons. These are the photoelectrons. The current that flows in this circuit due to the movement of this photoelectron is called the photocurrent. 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 So photocurrent will be observed here. All right? Now, what is the question? Intensity does not affect the kinetic energy of these electrons, of these photoelectrons. It does not affect the speed, how fast they are going to move towards the anode. The intensity of the radiation does not affect. The only thing that will affect the kinetic energy of these electrons is the frequency of that radiation or the wavelength of that radiation. However, the intensity usually affects the number. The intensity The intensity of the radiation, the intensity of radiation affects what? It affects the number of photoelectrons ejected. Even though it does not affect their kinetic energy, it affects the number, the amount of the photoelectrons that will be ejected. And the number of the photoelectrons ejected is what actually affects the photocurrent, the amount of photocurrent. Because the higher the amount of electrons that are moving, the higher the amount of the electrons that are flowing here, the greater the photocurrent that will be what produced. So that means that what the intensity actually affects is not the kinetic energy of the what? Photoelectrons, but it affects the number of photoelectrons and the amount of photocurrent produced. The amount of photocurrent produced. That is what the intensity of the radiation will affect. Not the kinetic energy, but the number of photoelectrons. And remember, current is the rate of flow of an electric charge. So the rate at which this guy flows will give me what? The current. That's the quantity of the charge flowing per unit time. So if the quantity of the charge, if the quantity of the photoelectrons increases, then it means that the amount of photocurrent will also increase. That's the meaning. If the quantity of these photoelectrons is increased, when we increase the intensity, then the amount will also what? Increase. The amount will what? Increase. That means that if I plot a graph of the photocurrent against the kinetic energy, if we plot a graph of current I, photocurrent, the photocurrent against maximum kinetic energy at different intensity values, we should have something like this. So this is intensity 1, I1, this is I2, this is I3 for the intensity. Why this is the current. So that means that if we increase the intensity, nothing will happen to the kinetic energy. The kinetic energy will still remain the same. But the current will be increasing. The photocurrent will increase, but the kinetic energy of the photoelectrons will not change. The only thing that will change is the amount of the current. So in this case, I1, I3 is greater than I2, I2 is greater than I1, meaning we increase the intensity. The intensity is increasing. The intensity here is higher than the intensity of the light here, higher than the intensity here. Then what happens is that what? The current will be what? Higher. But the maximum what? Kinetic energy will not change, will be the same value for the different intensities. That is what we are saying. So it is important you take note of this particular guy. I'm still going to come back to this this graph after talking about the final concept before we solve questions. So let's look at the final concept, then we'll go to questions. And what is that final concept? The final concept is called the stopping potential. Stopping potential. Right? So what is the stopping potential all about? I will use this diagram, then I will do the derivation here. In this case now, we can see what is happening here, that the electrons are trooping towards the collector. Right? Now, what if I don't want this process to continue? What if I want to stop this process? What if I want electrons to stop flowing to the collector side? what do I need to do? And that is where the idea of stopping potential is all about. So what I just need to do is, if you look at this setup here, the anode has a positive potential with respect to the cathode. The anode has a positive potential with respect to the cathode. From this our setup here, the anode is positive with respect to the cathode. Now, if we begin to apply a negative potential at the anode, if we apply a negative potential to the anode, if a negative potential is applied to the anode such that this anode is now negative, this anode is now negative with respect to the cathode. Of course, the cathode, the potential of the cathode is still negative. But we are now saying that what? If we apply a negative potential to the anode such that the negative potential at the anode is more than the negative potential at the cathode. The negative potential here, when it is more, if it is more, that's the meaning of that, it is negative with respect to the cathode. We are not saying that we are applying positive to the cathode. And you can also have that kind of setup where we apply positive to the cathode. The bottom line here is the fact that we want to stop these electrons from flowing. So if we apply a negative potential to the anode, what will happen? The electrons here are negatively charged. So that means that as the electrons are moving with a particular kinetic energy, once we have a negative potential at the anode here, then this negative potential will create a repulsive force. There will be an electrostatic force of repulsion that will be produced here, which will now what? Perform an electrostatic potential energy that will be going against this, our kinetic energy of the electrons. The electrons are moving with some amount of kinetic energy, but immediately we generate, and that is because this potential was positive before, so they can always go. But if this potential is now negative, then negative, this guy begins to push these electrons backwards. This plate begins to push back the electrons because they are of the same type of charge. It begins to push these electrons backward. It begins to push this electron backward. Why is he able to push the electron backward? If we continue to increase that negative potential, if we continue to increase that negative potential here, we are increasing the potential. This guy keeps pushing this guy. We increase the potential. He keeps pushing it back. Now, the minimum potential difference here, the minimum magnitude of that negative potential, the minimum magnitude of the negative potential on the anode that will result into pushing back the entire electron such that the kinetic energy is stopped. We are stopping the electrons from moving generally. That minimum potential energy is what we call the stopping potential. So if I apply a potential here, we call it the stopping potential. Let me say Vs. Stopping potential, Vs. We apply a potential, a negative potential to this anode. It will be pushing back these electrons here. That means that it will try to balance, it will create a potential energy here that will balance the kinetic energy of these electrons, that will go against the kinetic energy of these electrons. And as we continue to increase this negative potential, the more the electrons will be pushed back. That minimum magnitude of the negative potential that is applied to the anode to stop these electrons from moving is what we call stopping potential. So stopping potential, this is the minimum magnitude of the negative potential at the anode required to stop photoelectrons, from leaving the emitter, that is the cathode. So in order to stop it, there will be a potential energy that will be generated here. That potential energy is to stop the kinetic energy of the electrons from conservation of energy. That potential energy will balance the kinetic energy of the photoelectrons, meaning that the potential energy generated here, which is the product of the charge that is moving and that stopping potential, is what will be balanced by the the maximum kinetic energy of the electrons. And don't forget, the charge that is moving is an electron, so I can replace Q and put E. So EVS is equal to what? Ke max. EVS is equal to Ke max. So that means that the stopping potential, the potential that is needed to stop photoelectric effect, is actually the maximum kinetic energy upon what? Upon E. The maximum kinetic energy upon E. So what this VS? Another way we can see VS is this. These electrons are moving. But in that, when we conducted this experiment, we don't have that instrument that can be used to see the velocity with which these electrons are going, such that we can get the kinetic energy. We cannot visualize the velocity. Of course, you know that normally Ke max should be half mv max square, right? Where this v is the velocity, but we don't have an instrument to measure the velocity of these electrons. So how else can we determine the kinetic energy of these electrons? How can we find the kinetic energy? What if we try to stop the electrons from moving at all? Can we use that to determine the kinetic energy? Yes. And that's what we are saying here. That maximum kinetic energy will be equal to the product of the electronic charge, the charge of the electron, and the potential that is needed to stop the electrons from flowing. So this E here is the electronic charge. The charge of an electron, which is 1.60 times 10 raised to the power minus 19 coulomb. And this Vs is our stopping potential. Is our stopping potential. So our Ke max is EVS. So that means that in all the graphs that we have been plotting, we can go and replace Ke max with EVS with the stopping potential quantity, so that we will see how the graph will now look like. For an instance, in this place, if I plot the current against potential V, if I plot current against potential V, then this value here will be our stopping potential. Because it is at this value here, current against potential V, it is at this value here that, what's it called? Of course, it's the negative. It should be negative side. But let me just explain it, because this guy is a negative value. What we are saying here is the fact that what? Even when we increase the intensity, we know that what? Kinetic energy will not change. Similarly, the stopping potential will not change, because kinetic energy is a function of what? The stopping potential. Let me use VS. I use VS. The stopping potential. So we can have the graph like this. Similarly, if I go to the other graphs that we have before, from the Einstein equation, we have that Ke max is equal to HF minus HF naught. Now, what is Ke max? Ke max is EVS. So EVS will be equal to HF minus HF naught. Divide all through by E. That means the stopping potential is H over EF minus H over EF naught. So that means that if I plot the graph of VS against F, if we plot the graph of stopping potential against frequency, if we plot the graph of stopping potential against frequency, it's going to be a straight line graph. It's going to be a straight line graph too. And from there, the slope of the graph will be H over E. The slope of the graph is H over E. On the y-axis, which is the VS axis, the graph will cut a point which is minus H over E. And where is it cut in here? It is our F naught. If I plot a graph of VS against F. So it is still the same graph. The only thing that would differ here is what the slope would be and what the intercept here would be. So if I plot stopping potential against F, I'll still have the same straight line graph. If I plot it against 1 over F2, it's still the same pattern, just that this is what the slope would be, and that one there will now be C. That will be HC over E. While for the other, for the intercept, it will be minus AC over E if I plot VS against 1 over lambda. So this is everything you need to know as regards photoelectric effect, and I hope everything is clear to you. So we're going to be looking at different questions now. We're going to be solving problems on this phenomenon, and in order to solidify our understanding of this particular topic, which is a very, very essential topic in physics as well as in chemistry and other physical science courses. So let's see some questions, interesting ones, and I'm going to have it so clear to us, because we have just been writing the equations and doing some conceptual explanation. Now let's now see actual problems together. All right.